also. In with open mic also you can ask, and on chat box you can also ask. That will be very helpful. And also I will like to ask question between the presentation, and I will be very much thankful for you, or if you respond to them, it will be very kind for you to, for your understanding also. So with that simple introduction, let me start my presentation. And so my screen should be visible right now. If it is visible, someone can give me audible nod. Is my screen visible to all of you?
Yes, yes, it is possible.
Okay, and my voice is coming clearly, na?
Yeah,
Okay, thank you. So, as Guru Raja told, I am Mohit Joshi. I am doing my PhD in Banaras Hindu University. Hopefully, some of you know that university. And my topic right now is quantum computing, especially in quantum cryptography. And I'm very thankful for the opportunity that Shastra University has given me to present some of my recent work and some of my understanding in the topic and the subject to all of you. So, like I thank you to this faculty development program for giving me this opportunity. So, I would like to start by uh, uh, giving you the outline of what will be the outcome of this lecture, what you can expect from this lecture. First of all, if you have never encountered Grover's algorithm, you will understand it intuitively. You will gain an intuitive understanding of that algorithm. And if you are already familiar with algorithm also, especially I'm talking about only Grover's algorithm, not other variants. If you are familiar with the algorithm, then you will also get some basic insight, or gain the mapping, as if you have all. If Grover's algorithm would not have been made today, you could go home and made it rediscover it yourself. I will also describe much more hands-on mathematical framework of this algorithm that will help you to understand how other quantum algorithms work, and how in general you can design or take advantage of properties like superposition to your advantage. And I will also I would also present you how can you convert that mathematical expression to actual circuit design that we do in our daily basis. Actually, at the end of the day, we are going to do the circuit design to validate our theories. So this is the outcome. And with that, I would like to know how many of you already know Grover's algorithm. How many of you have heard of Grover's algorithm, or how many of you have known Grover's algorithm? Can you can type your answer in chat box. It will be good. So two guys know Grover's algorithm. How many of you don't know Grover's algorithm? Everybody knows Grover's algorithm. Oh, okay, two guys. Two people know Grover's algorithm and other don't have the answer. It's okay. So we will start by. Sorry for a second. Okay, we will start by. Okay, this is the content of the presentation. I will start by introduction, then Grover's algorithm, intuition, and all. And without doing further ado, I'm going to start the introduction. Sorry, my laptop is little bit lagging. Sorry for that. Okay. So, what does the Grover's algorithm do? What is it for? It is very simple if you know Grover's algorithm. So, suppose you have an unsorted database of 10,000 elements, and classically you want to find the target value. Then, on average, you need at least 5,000 comparison to do that. On average, you can get lucky and get it in the first try, or you can be very unlucky and get in the last try. But on average, you can get it in 5,000 tries. So, how fast can quantum computer do it? Quantum computer can do it in under root of 10,000, that means 100 steps only. That means this gives a quadratically fast speed up, or quadratic speed up over any known classical algorithm, specifically on unsorted data structure. So unsorted, this algorithm is not just for unsorted databases, it's for unstructured data spaces, and it can do search on unstructured data space quadratically faster. What I mean by unstructured data space is much more than only a database. It is any place you can apply brute force is the place you can apply Grover's algorithm. That too with quadratically fast speed. So why is it important? Why unstructured search is so important? Unstructured search is so important because it is being applied in many of the well-known problems that are still out of our reach of tractability or solvability, not exactly tractability, solvability. So feasible solvability. AES algorithm is one of the example where AES algorithm is based on the primitive that keys of 128 or 196 or 256 bits will be infeasible to search brute force. That's why AES is so secure. But with quantum algorithm, we can do it in tractable time. So AES will not be secure if a full-fledged quantum computer can come and we can run Grover's algorithm on that, but it is a little bit far than we assume. Genetic sequencing is another example where we have to search among the genetic sequences and find the suitable match. It is sort of pattern matching. And solving Boolean satisfiability, another example, and another is optimization problem without gradient. Using gradient. Gradient is the most important algorithm of 21st century, I think, after obviously Fourier transform. So gradient has like uh, converted our understanding of machine learning and deep learning models, and that's why gradient is important, and that's why if Grover's algorithm is replacing it, it is also important. So, in general, what I'm saying is that some of the well-known problem in NP class are being converted to BQP class. Now, BQP class is another class of complexity. I am sure that you have heard of complexity classes like P, NP, and like NP complete and NP hard. So, this is another kind of class which is specially designed uh, like sort of like BPP class. It is designed for bounded quantum polynomial problems, which a problem we can solve on quantum computer in polynomial time with bounded error. So now what is the Grover's algorithm? So Grover's algorithm is very simple algorithm. We start by uniform state of 0 of all the qubits, then we apply equal superposition, then we apply oracle, and then we apply diffusion, that is also called inversion or inversion about mean. And in step 4 we repeat step 2 and 3 k times. So this is as simple as it gets. This is the Grover's algorithm. But the question is how it is doing that and how it is performing. What is the structure of a oracle? What is the structure of diffusion? And how many times is k times to get the correct answer? So for that, I will like to discuss these points in three key aspects. First, I will discuss the intuition behind this algorithm. Then I will discuss the mathematical structure of this algorithm, and at last we will construct the circuit from these mathematical representation. The presentation will start slow, and then it will get on math heavy as it goes. So pay attention. But I'm definitely sure if you pay attention, then you will go home today and think of Grover's algorithm as if you could have come up by your own if you have the right tools to develop it. So intuition behind Grover's algorithm. So suppose I say what is the complexity of algorithm, then when we say the complexity of algorithm is n log n or n square or n cube, it is not an independent quantity. It is based on the assumption of what kind of computation model you are using. So whenever we talk about the complexity, we also should know about what is the underlying computation model behind it. So if a computation model is such that it sees one input at a time, then how many times should it see the list of size n? That means if we have database of size n, and then how many comparisons should a model make? If it can make one comparison per iteration, then can somebody tell me how many times does it need to compare if our computation model is like one comparison at a time? Okay, to set the premises, I can start by simply saying it. If the model compares one element at a time, then at most it takes n elements at a time, and that's where the complexity of on comes in. Okay, so if simply if a model sees one element at a time, then it can compare n uh, times and get the answer. Now if I tweak the model, if our model compares two elements at a time, how many times should we see the list? Can somebody give me the answer now? How many comparisons will it make if the model is seeing two elements at a time? Okay, two elements at a time. Can somebody, is somebody saying in chat box? Uh, 2 power n. Yeah, it does. I think n is a number of qubit, I think you are taking. If a model is taking n, seeing two element at a time, then it will simply need n by 2 n by 2 times it will see the database, because every time he sees two data elements, then it will be n by 2. Similarly, if a model sees four element at a time, then how many comparison it will take? Now I think the trend is easy to see. uh, yeah, somebody give the not two. Now what will be if and our computation model is seeing two element at a time, how fast can it like how many times should it compare to get the answer? Can anybody tell me? Based on the progression, first it was one element at a time, it was n times he has to compare. Then two element at a time, it is n by 2 times. Now it is four element at a time. If it's seeing four element at a time, what will should be the answer? In chat box, someone can. Yeah, exactly, n by 4. Thank you, Dr. Anand. So that is exactly the answer I was looking for. So if a model can see four element at a time, it is simply n by 4. So if a model can see all the element at a time, then I think answer is clear that it will see all the element at a time. Then it can get the answer in one time only. Okay, this is interesting. If we can find that model, we can get the answer in one time only. So the question is, does such a model exist? Can a model see all the can a computational model be existing that can see all the element at a time? And answer is yes. Quantum computing can see it using the principle of superposition. That's the first thing we learn in quantum computation is principle of superposition. We can superimpose, and all the inputs are in equal superposition. So quantum computer in essence can see all the inputs. So this point I made is clear to all of you, right? So according to according to this argument, the quantum computer can see all of the input and it can search also in constant time. That means the complexity should be O of 1, not O of under root n. So where does this under root n comes from? We will understand and argue about it now. So where does this under root n comes from? So the problem is that in constant time, quantum computer can find it. We cannot find it. So we have to somehow find a clever way to build a clever way that can extract that answer for us. This is the premises of Grover's algorithm. This is what the Grover's contribution to the field of quantum computation was. Everybody knew that you can quantum computer can see the answer in constant time, but nobody knew how to extract it. So how how did he do it? Suppose, let me explain the figure here. Suppose we have an equal superposition of database. There are elements on the x-axis. I have drawn the element cat 0 to cat n minus 1. These are n element of data space, and tau I am giving that is the target state, that is state to be found. On the y-axis is the amplitude of these values, and as the first step of Grover's algorithm is equal superposition, then we will simply superimpose all the state, and this is what the diagram is showing. On the left hand side, this is what the diagram is showing, that all the amplitudes are equal. If we see mathematically, it can be represented in matrix form, and I think you all are familiar with that. So we start with a constant zero state, that is one, and all of followed by all of the zero here, and uh, then we convert it into equal superposition. That means all of the values are one with that normalization factor. So this is what mathematically this transformation means. We start by zero, and then we converted it to one. So this is the first step. Now let me add some more elements to this visualization. First is equal superposition. I will mark it is just for visual representation. Nothing fancy is happening here. I am just marking the state to that is our target with a different color. Now tau is different color, and we know that we have to find that state, and we will keep track of that state and how that changes. Okay. So, and another quantity that I want to add here is the mean of the data. So if all the values are in equal superposition, suppose if we have three values and all of them are 5, then the mean of the or average value of that will also be 5. So 5 plus 5 plus 5 upon 3, that means mean will be 5. I think that is basic mathematics. So mean will be this line only. So Grover's algorithm take advantage of that mean and manipulate that mean such somehow that it can invert later around that basis. So what the second step of Grover's algorithm is? Second step is implementing the oracle. So implementing the oracle means we will mark the state, this state, and in implementing the oracle in especially in the sense of Grover's algorithm means that we will invert this state tau, and which can easily be done by strategically placing the z gate on the tau state. That means the state will look like this. So it is important to note here, sorry for the overflow. It is important to note here that the state previously was equal superposition like this, and now it has gone from this to this, where all of the states are in equal superposition, but from the for the middle tau state, which is now in -1 state, which is also equal superposition. So converting this, we see that the line of the mean has gone down. So now before we are adding 5 plus 5 upon 3, which whose answer was 5. Now it is 5 plus 5 minus 5. So some cancellation happens, and then the mean comes out to be smaller. I think it will be 1.33 in our given example. So in the diagram, this is being shown. The mean has dropped. So now applying Oracle just once, quantum computer has found the answer. He know which is the answer. He know if we can see the amplitude, we can exactly know which is the answer state. But we cannot extract this answer, because we know that if we measure that, we get the square of amplitude, which is square of negative number is equal to square of positive number. That means we will see no benefit of applying oracle here. So now what Grover does to amplify this is Grover's algorithm specifically. So what he does is that he invert about mean. He call it diffusion operation or inversion operation sometime. He invert about mean, and sorry for this overflow again. This inversion, what it does is minus every element by its mean value. So 1 is minus by 1 minus 2m. Suppose m is the mean. 1 minus 2m, 1 minus 2 every element except the target value, which is minus 1 minus 2m. So all we can see, all of the values will decrease except the target value, which will whose amplitude will increase. That is shown in the in the figure also. When you invert about mean, that is minus all the minus mean, constant mean from all the values, then only one value, the target value, will increase because of negative sign, and all other values will decrease. This was the idea of Grover, to use a mean or invert about mean to get the answer. So keep this transformation in mind. It is converting this into this. Now, if we move forward, we can see that this can be simply inverted. That is also covered in the part of diffusion operation. We simply convert the sign of everything, and we can see clearly everything is getting negative except the target value, which is getting positive. But still, it is getting good answer, but still it is not the optimal answer we can get from the Grover's algorithm. So what is the this is we are getting. Remember, keep in mind that this is we are getting by applying Oracle only once. So only once if we apply Oracle, we can get certainly get some advantage. Certain see some values that are increasing, but still we want to get the answer with highest possibility or highest probability we can get. So what we do from here on is repeat this step. So in step 4, we repeat step 2, that is apply Oracle. That means we are in the at the same step that we are at the start. Then we apply a diffusion again, two process of diffusion. First apply diffusion, and then Z gate to invert the phase on all the gates. So this is how inversion is being performed. Now if we repeat this step, we can get this probability as low as we want. So this is what we are getting in the transformation, and bingo, you have found the correct state. Okay, so this is the Grover's algorithm in a nutshell. If this confuses you somehow, that interpretation, then we can take a moment and understand if something is not being understood by you. Okay, some if there is a question at this point, you can ask right now. If this representation or you don't understand this method that I use. Okay, so everybody is clear about that. Okay. Okay, then we can move forward. So, what are the open questions now? So, if we recap the Grover's algorithm, we know that we start by zero state, and then we apply equal solution, then oracle, then diffusion, and then step 2 is repeated k times. So, and we also know now intuition that how oracle works and how diffusion is amplifying that about the mean. It is all about where the mean is and how we manipulate that mean using oracle. So now, what are open questions? Open questions are okay. I understand Grover's algorithm. Okay, fine. But what is the structure of Oracle, and what is the inversion operation? What is the structure of that? How mathematically? What metrics are they? How do they look like? And if you already know what is the structure of Oracle, how do they form? Why does it look like it looks like? Okay. And second question is, what is the optimal number of k? That question we still haven't answered. How we get under root n times the complexity? Okay. So we will answer this question now. Finding oracle. So first of all, we'll start by finding oracle, which is we take a very simple oracle here. The exact oracle will depend on the problem statement, obviously, and its circuit will depend it vary vastly based on the type of challenge you are facing and the problem you are solving. But in general, what the circuit of algorithm look like, matrix of this look like. Let's build it. So we know what Oracle does. Oracle simply does, if we take we are I'm taking a simple example of like 4 cross 1 matrix, that is two by two situation, 2 qubit situation. So in simple scenario, what Oracle does is take from 111 to 11 minus 1 state. Okay. So we just have to find a matrix that can convert 111 state to 111 minus 1 state. If you keep basic mathematics in mind, basic matrix multiplication in mind, it is very simple operation. So how does it look like that? So if we simply say that it do not need solving a sort, we can see that from structure that if we multiply this sort of unitary in sorry identity looking like matrix where every diagonal value is one except that the value which is target value, then we will arrive at that matrix only. So if anybody has confusion in that and you have answer question, you can ask in chat box. Uh, okay, so everybody understand how the structure is formed. It is a simple representation, right? Okay. So now let us do something with that this structure and simplify it more. So we know that it is formed of like unitary matrix somehow. So we can decompose it into unitary matrix also, like this. Okay, this is a unitary matrix minus 2 times of this matrix, where only element that is present is this one state, and you can easily verify that this is the correct representation, that is identity matrix minus 2 time of this matrix. We can even simplify this representation using more notation, like identity tau is what I am representing. Like or my oracle, it is variation of identity matrix that's why I've used identity tau. This is moving forward we will use this consider this as a oracle. So we can represent it as identity matrix minus this matrix and this vector multiplied by this vector, which is nothing but this is the state we are searching now. This is tau and this is also tau. This is cat of tau and this is bra of tau. So if we represent it, then we can say that the general form of oracle can look like identity matrix minus 2 time of tau and cat tau into bra tau. And I am sure that this representation you have seen many times if you have known Grover's algorithm. So that is how we represent, we arrive at that structure. So now, similarly, let us go forward and find our inversion circuit. So, what is the form of inversion circuit? Inversion circuit, despite irrespective of what algorithm or what problem you are trying to solve, diffusion circuit will remain the same in all the cases. So, what is the purpose of diffusion circuit? Purpose of diffusion circuit is simply to get from this state that we have obtained from oracle and minus some constant unit, especially mean from that, and this will give us the amplification advantage. So how do which matrix can do this? A matrix that can do this is this matrix. Okay, every element is 1 minus every diagonal element is 1 minus n except, and every non-diagonal element is minus 1. So this is also a variation of uh, like identity matrix, and what identity matrix forms, it is also simple. It is, oh sorry for the overflow, it is identity matrix, I can represent it. It is identity matrix minus m times of a matrix which have all the values 1. So this is only identity matrix minus m times of all the values ket of 1, this vector and this vector, which is multiplied, giving us all the values 1. So this vector is also familiar in terms of problem. This vector is what we call equal superposition. Given that we equally take the value of properly substitute the value of n, we can get what we get is 1 is the equal superposition of our database. That is when what we created in equal superposition. So uh, this is what the structure of diffuser look like, and this is a structure what is the structure of diffuser look like always, regardless of the case. Now regarding the value of m. if we solve this equation, we should get a matrix, this especially this matrix, which is a unitary matrix in nature, because we have to implement it on quantum gate also. We are not doing some just matrix multiplication here. So for unit this matrix to be unitary, only values it m can take is 0 and 2. So we give a non-trivial value 2. So using that value, we can represent this state as a this diffusion as identity matrix minus 2 times of psi vector into psi ket psi into bra psi. So this is the representation of oracle and inversion operator, and this will be used heavily when we calculate other things, especially in number of iteration, and this will come in handy. So I would like, if you want to keep tab of it, you can write it down somewhere in your notebook. I can represent this also. This is a structure of oracle. You can write it down right now if you, because it will get referenced later. So hopefully you have written down, and this is the structure of like diffuser operator. We will use this also later. Now the third question is, what is the optimal number of iteration? That is the most important question. That is how we will find when to stop an algorithm, how many iteration does the algorithm take, which will decide how many oracle calls the algorithm will take, and which will decide the complexity of algorithm in terms of comparison. So let us start by simplifying the tool of analysis, because as we seen in the previous graphical analysis, the mathematical analysis of that was very cumbersome. It was so cumbersome that it was not even, it was overflowing my slide also, and I'm sure I might have missed some plus minus in writing that also. So that analysis is very cumbersome, so we can't use that analysis and tend to find the number of iteration pretty easily. So there is another tool we can use to analyze the Grover's algorithm with another lens, and it will open another picture of representation for Grover's algorithm, and we will use that for finding the number of iteration. So this we start by assuming a data space of size n with n qubit representation, that is n is equal to 2 raised to power n, as is custom in quantum computing to take any value which is in the power of number of qubits. So if we have equal superposition, we can represent the data set as like this. Okay, it is all the values of 0 1 this, and 1 by root n. This representation, I'm sure everybody is familiar, and I don't have to like, if I have to explain this, if somebody has a doubt, I can explain. I have one question here. Okay, this representation is okay. Yeah. So now the idea is that if we are solving Grover's algorithm, we can use some native methods to differentiate that data set even further. So what we do is think of this data set in two different or disjoint sets. One set contain the element that we need to find, and second set, that is gamma, contain all the elements that we don't need to find. So if we differentiate this database in two type of element, X contain all the element, and if we differentiate it in the element that we need to find and all the element that we don't need to find, then we can represent the same data space, the same data structure, or same database as different entities of some value, some normalization factor of gamma, and some normalization factor of tau. So this is the representation we are going to use, and it is advantageous to see here that this representation can also be visualized at this in the power of cos theta and sin theta, right? So if we represent this value 1 by under root 2 raised to power n as sin theta, then ultimately the coefficient of gamma will come to as cos theta. So this with theta is obviously uh, like sine inverse of 1 by under root of 2 raised to power n. So this is the representation that we are going to use, and the written equation here means that now the data space can be expressed in two different vectors also, that is gamma vector and tau vector, that can also be seen as a basis for basis for this data space or database psi. That means if we, and these are disjoint, and you can also prove that these are orthogonal to themselves also. So what I mean to say that is, if we represent it in a space where tau is orthogonal to gamma, then psi will come somewhere in between. Okay, this representation I'm sure you have seen if you have known Grover's algorithm. Previous representation I'm not very sure about, and this representation I'm sure that you have seen. So here we are, the equation we have formed, the tool we have made is have enabled us to represent the data space or database in different format. Okay, so done. Okay, so I think I'm going too slow right now. So this is the data in span of gamma and tau. Now this is where we do the magic. Now we simplify the Grover's algorithm, Grover's operator only. Grover's operator is what, when oracle and diffuser are multiplied together, we get the Grover's operator. And what is the structure of Grover's algorithm? We have previously verified and derived that the structure of I psi looks like this, and the structure of I tau looks like this. That is exactly the Grover's algorithm. And this Grover's algorithm can then be simplified even further to give us the answer of Grover's operator in the matrix form, which is this matrix. If you know this matrix, if you are from computer science, you know this, or if you are from mathematics background, you know this. This is a simple rotation matrix. Okay. So this rotation matrix, and that is what the Grover's algorithm is doing in the span of gamma and tau. It is rotating the data space psi in the span of gamma and tau. That is what the Grover's algorithm is doing. So this is what the Grover's algorithm looks like, where in the span of gamma and tau, where this was the data, and we convert it. First we apply it is I tau. Sorry for the representation. It is I tau, that is oracle. If we apply oracle and then apply this, we get the Grover's operator. And when we apply it recursively, or when we apply it iteratively, we get closer to the value of tau. Now my question is, if you understand this derivation properly, it assumes some things. It is based on what we have previously derived. If you want me to derive it here, I can go step by step on this, or if you want, if you understand it, we can skip it also. So in the chat box, can someone tell me if you want to derive this expression, or should we skip this? If anybody want me to derive this expression clearly, if they don't understand how derivation is going on, because it assumes some values of some predicaments. So it is okay then, no? I don't need to explain this derivation, right? Okay. You can answer in chat box also if you. Uh, okay, that will conclude our presentation quickly then. So this is the derivation which we have used to arrive this Grover's algorithm. Now we will use this derivation to implement the find out what is the optimal number of iteration. So that was one iteration of Grover's algorithm. We have to apply Grover's algorithm k times to the data space. If we apply Grover's algorithm k times on this data space, we can simplify it into the vector form of cos 2k plus 1 theta and cos 2k plus 1 sin 2k plus 1 theta. This is the simple matrix multiplication which we get after multiplying Grover's algorithm k times. Because Grover's algorithm was a simple rotation operation, it also simplifies for the power of k. It simplifies simply to cos 2k minus sin 2k, sin 2k and cos 2k. This is very it got simplified because the structure that we are using simplified the problem very much. And now the problem is very easy. It is the the bottom value sine 2k plus tau. This represent what is the amplitude of corresponding to tau value. So we want it to be 1. Okay, we cannot get exactly 1, that's why we approximate it. And if we simplify this expression, we get the value of tau as this only. Okay, value of k naught, the optimal value of k will be pi by 4 under root of 2 raised to power n, where 2 raised to power is equal to capital N, that is the number of data elements in the database. This is how we prove that Grover's algorithm takes complexity of O under root n, which is quadratically faster than any of the algorithm in the classical domain. So this was the simple derivation of that understanding. Now from this, we know that how Grover's algorithm look like. We know that how Oracle looks like. We know how many times we have to apply the Grover's algorithm. So how do we know the mathematical structure Grover arrived at? But how did he convert that structure to a quantum circuit, or how in the modern era we are converting it into structure that contain X gate, Z gate, and all that gate only? Because the structure previously discussed of Grover's algorithm is not very intuitive. It is this structure was not easily implementable in the Grover's in the circuit form. We can't say what will be the circuit structure of that just looking at that. So we have to derive it. So what is the circuit implementation from Grover's operator? This is the circuit implementation of the Grover's algorithm. We start by equal solution H gate, then we apply oracle based on the value of tau. If tau 1 means if the bit is uh, if the bit is 0001, then if the bit position is 0, then x is applied. If bit position is 1, x is not applied. We will understand that when we do our derivation also. So this is the structure of Grover's algorithm. This is how initialization, oracle, and diffusion looks like. And this oracle and diffusion is repeated k times. We now know the value of k. We can just repeat this oracle and diffusion k times, and we'll get the answer. So the problem is, how did we get to that structure? We can't imagine that structure from that equation. So this is the derivation using which we arrive at that structure. It first we implement the oracle. I tau is the oracle, which we now from previous discussion we know that it is equal to I identity matrix minus 2 times of ket of tau into bra of tau. So what we do here is come out of tau such that it gives us identity value. So tau is something like, I can explain it here also. Tau is something like something like 0010 suppose, and we are converting that into element that is all one. So from this I can it come to all one by just applying X gate where the input is 0, right? If it was tau, if we apply X on the bit where the value is 0, we can get X on this, X on this, X on this. We can arrive here. This is what I'm doing here. I take this tau and then apply X selectively raised to the power of tau 1 to tau n, where tau n represent 1 if the bit corresponding to that value is 0. If the bit corresponding to the target state for that value is 0. So if we do that, tau can be represented like this. Okay. And similarly, bra tau can also be represented like this. Okay, now this is a representation. Now what we can do is this is identity matrix, and we know that x multiplied by x is also identity. So if we are given identity matrix and we apply x left hand side and then we apply x on the right hand side, then it will be identity matrix only. It will be of no change. So that means that this is identity matrix, and if we apply x on the left hand side and if we apply x on the right hand side, we can get the same value. This is identity only matrix only, but the representation is changed. Now what is it help me to do is we can take this part and this part common from the left hand side and take this and this part common from the right hand side. What we remain inside is this matrix, that is identity matrix minus 1 uh, cat 1 and bra 1 of multiplied whole multiplied by n, which is the size of state, which can be represented by this element. And if you multiply this, or if you see this matrix 0 1 0 0 0 0 1 0 0 0 0 1 minus of this matrix, which is all 1 multiplied by all 1, you will get, this is the simple structure of sorry all this is a simple structure of CZ gate. Okay, so this is a structure of CZ gate. That means this, what we have written here is CZ gate. So now we know how to implement this oracle. We can simply apply x selective x we can apply, then we apply CZ gate, and then we apply X gate. This is a simple reconstruction of a circuit from the expression. Yes, and I'm sure that you will encounter these kind of structure more in other problems also. And this is the method with which you can represent, or you can derive your circuit if you are ever stuck in the problem that I know the mathematical formation and don't know the structure. This is the representation we use. So now we move forward in the next slide. We represent how uh, this psi is represented. That is diffusion structure is represented, and similarly to the oracle, we start diffusion operator. We, what we do is, this is psi all one. We can convert it into this state, zero state, by applying because psi was actually in first place, it was Hadamard gate into zero state, so we can write that also from this to this and from this to this. Okay, from left this get and this bar. Okay, sorry. So now if we apply convert this I 0 to 1, we have to apply all the x gate on this 0 gate, we can convert it into 1. So this is how I have mashed the similar structure that we have discussed previously. This is a same different representation of same quantity. Now this representation can help me to build a circuit in the similar fashion. And again, we know that identity, if x multiplied by identity multiplies by x, is also identity. And also if we multiply h on both sides, it is also identity, then there is no issue. So what this big fraction is written is identity matrix only, for with fancy notation. So what we can do here also is take common out from this and this. We take common from the left hand side and take common from the this and this. We take common from the right hand side, and what we have got in the middle is this. So this middle value is what we get in the iteration, and this is then again the CZ. So again, the implementation of or diffuser will look like all the H gates as much as you have, all the X gate. Here no condition is applied, so all the X gates are applied, and then all the CZ gate. Okay, and then all the X gate again to revert that, and then all the H gates. We have formed the structure of a Grover's algorithm from the mere mathematics of what Grover's discussed. So this is how the structure of any quantum algorithm is formed. So now, recapping the circuit diagram, this is what we discussed. In initialization is simple, we apply all H gate. Now we applied simple selective X gate, and then CZ gate, and then X selective X gate again, and this is the structure of a diffuser operator. So I hope it is up till now it is clear to everybody. Uh, Gamma is equal to 1 0 is right. Uh, can you elaborate your question? Gamma is not 1 0. Gamma is not equal to 1 0. Gamma is all the element that are not in. Sorry, I didn't saw the question. Let me clarify that again. Uh, Here, gamma is not equal to 0 if we are differentiating the set. If we say that we have 2 by 2 case, then all the elements that we have, all the elements we have are 0 0 0 1 1 0 and 1 1 in this format. And suppose we have to find this element, then tau will become a set that contain only this element, and gamma will become the set which contain all the other elements. So it is 0 0, it is 0 1, and it is 1 0. That's how it get orthogonal also. It is orthogonal and it is uh, disjoint also. These sets are disjoint. That is what I meant to say when I say gamma represent all the elements that are not the set. Any other question about that? Okay. So I hope the presentation, I hope the explanation of the algorithm was okay. If anybody has questions, then you can ask, especially regarding the mathematics. We can go on the problem of the this domain and much more in when we go in hands-on. For right now, this is the mathematical structure of Bohr's algorithm. Does anybody have problem? Okay, nobody has problem. So let me conclude this structure with this presentation by discussing some of the future scope and research direction. Purely, if you are discussing about Grover's algorithm, what are the if Grover's algorithm is made, then what are the research direction in open in this area? So after the Grover published his result in I think 1996 or 1998, after that. There are many variant of Prover's algorithm, even up till to the early of 2024 or I think 2025 also. I saw some paper which are very good, and they were variant of Prover's algorithm, and there is much more thing to find in just one this simple area of Grover's algorithm, as much as there are other things to do. So in Grover's algorithm, we know that now we know that there are many variants. First is exact Grover search. So this search the Grover proposed was approximately correct. That is, it gives answer 99, 98 like that, and for very large value, it gives absolutely correct answer 100%. But for small values, it gave a little bit of error, 0.1, 0.01% error. That error was resolved in another variant of Grover's algorithm, which is exact Grover search, which is also called Long's version of Grover search. He proposed a method where that diffuser is converted a little bit such that this algorithm works perfectly in all the cases. You get 100% probability in all the cases. Then again, Grover's and with help of I think one other scientist proposed partial quantum search, which is distributing sort of the start of how do you distribute the structure. In Grover's algorithm, you have to have the equal summation of all the qubits at once. If your database is very large, then the number of qubit or number of qubit that you have to keep superposition at once is too much. You cannot divide and conquer this Grover's algorithm because you have to keep the superposition. So he proposed another method of doing that by using partial Grover search, where you can divide it in components. So half of components can be divided divisible in that quantum search, and Grover proposed it, and then many variations of this are also been have also been proposed. Another method is depth optimized search, which is based on much more modern notion of uh, Grover search, because most of the Grover search and in many phases we discuss about the complexity in terms of number of comparisons. So that is because this is what classical computation does in all of the searching algorithm and all of the sorting algorithms and other algorithms. We assume our model is comparison heavy, and that's why we write our complexity in terms of number of comparison. O of n is written, that means n times on average it is n time that it needs to compare. But this is a classical notion. Quantum version means algorithm also need quantum notion, and we now know that the circuits are much more elegant if they are lesser in depth. Okay, depth is volume is one criteria. Sorry, number of qubit is one criteria with which we can judge our algorithm. But depth is also another criteria. Depth is not equal to the number of gates that are being applied, and depth uh, is number of parallel gates that can be applied in a circuit, and it is much more to the heart of quantum computing notion. And one paper came, it was very good paper, it was published in PRA, I think, and it discussed the depth optimization aspect of this Grover's algorithm. Can we move further and optimize this depth? And then again, there was recent versions of distributed search and exact distribution search based on the partial search algorithm. And there are many variant of this algorithm that are coming still now that are actually useful and in many respects. So Gover's algorithm is still in full fledged, and you can research in these directions. And first of this, and second is its improvement, its application in the domain of in other domains. So improving quantum search under noise condition in one of the uh, main objective right now, as we are living in this era, and we know that Grover's algorithm as it is not implementable for much more than I think 10, 12, 20 qubits, which is much more to say. But for practical purpose, we 20 is too much. For practical purpose, we need noise to be less because hardware is noisy. So this is an area of improvement right now. How do you negotiate these noises? How to error correct these noises? How do you use Grover's algorithm in advantage? Because it is shown that in some of the under condition of some of the uh, errors, for example, amplitude or some other errors, the maximum your optimum value can be reached before the value that is Grover's algorithm predicts. So it is also an area of improvement, and then application of for quantum search in various domain. In cryptography alone, there are many application of Grover's algorithm. We are every day proposing methods that can um, enhance some area, and we have also proposed a quantum searchable encryption based on Grover's algorithm. So uh, these are the main area of improvement of future scope, and I think and these are the references, and I would like to thank you all for this presentation. We'll meet again after the lunch break. And if you have any question right now, you can ask regarding that, regarding future scope or regarding application of global algorithm, or any question in general. If you want to ask, you can ask that question right now. Was my presentation helpful, or was it too boring or too mathematically oriented for you guys? Someone. Okay, no answer. So I think Guru Raja.
Mohit.
Yeah, I think I would like to conclude my first presentation.
Okay.
Okay.
Thank you, Mohit Joshi, for your insightful session on Grover's algorithm. We truly appreciate your time and expertise. We will now break for a tea and kindly rejoin the session by 11 a.m. using the same Gmeet link. Thank you.
Okay. Thank you.